Rational inequalities. Our objectives: solve quadratic inequalities algebraically and solve rational inequalities algebraically. The steps for solving rational inequalities with a sign chart. Make one side of the inequality 0 and the other a single fraction. We'll factor to find the critical numbers. Put the critical numbers on a number line. Write all the factors to the left of the sign chart. Test the intervals and critical numbers. Determine the appropriate labels and record the answer in interval notation. Critical numbers will be the zeros of any factors appearing in the nonlinear inequality. Solving rational inequalities. Let's solve x plus 1 over x minus 4 is greater than equal to 0. This is already in factored form, so we'll draw our number line. And the critical values come from setting each of those factors equal to 0 and solving. So our critical values here are -1 and 4. Now we're going to place the factors that appear to the left of the sign chart. Now I'm going to test each interval. This is the first interval I'll test. What is a number over here that we could put into the sign chart to test? Something to the left of -1. Let's say -3. If I put -3 into this factor, -3 plus 1 is negative. If I put -3 into this factor, -3 minus 4 is negative. And a negative divided by a negative is positive. So any of the numbers that are in this interval will act on that inequality in the same way. It will make it positive. Let's pick a number in this interval, maybe a 0. If I put it into this factor, 0 plus 1 is positive. If I put it into this factor, 0 minus 4 is negative. And a positive divided by a negative is negative. How about over here? If I test something over here, maybe a 5 or a 6, 5 plus 1 is positive. 5 minus 4 is positive, and a positive divided by a positive is positive, or positive times a positive is positive. Really, if we have an even number of negative signs, it'll turn out to be positive. If we have an odd number, then that interval will end up to be negative. So what kind of intervals am I after for this? I am after intervals that are greater than or equal to 0. This means positive or equal to 0. For us, this is a positive interval, and this is a positive interval based on the results of our sign chart. So I'm going to use those two intervals, and now I need to decide how to treat the boundary points. Will -1 make this a true statement? Will it make it positive or equal to 0? Well, if I put a -1 here, it makes the top 0. Put a -1 here, it makes that a -5, and 0 divided by -5 is 0. And because we want things that would make it equal to 0, we will include that. So we'll put a square bracket. Now, let's look at 4. Would we include 4? If I put 4 here, I would get a 4 plus 1, which is 5. If I put a 4 here, 4 minus 4 is 0. And 5 divided by 0 is not 0. It's undefined. So I can't include 4 in my solution set. My solution is going to be negative infinity to negative 1, union 4 to positive infinity. Let's solve this rational inequality. X plus 1 times x minus 3 quantity squared all over x minus 5 is greater than equal to 0. We already have it in factored form, so we'll go ahead and write out a sign chart. The zeros from each of those factors are negative 1, 3, and 5. Remember, we find those just by setting each factor equal to 0 and solving. Now I'm going to write each of the factors to the left. X minus 3 is squared, so make sure that we use that, and x minus 5. All right, we're going to test this interval, maybe a negative 2. Negative 2 plus 1 is negative. Negative 2 minus 3 is negative 5. Negative 5 squared is a positive 25. Negative 2 minus 5 is negative. Here we have an even number of negatives, so this results in a positive interval for us. Now we're testing the next interval. Let's test a 0. 0 plus 1 is positive. 0 minus 3 is negative 3. Negative 3 squared is positive 9. 0 minus 5 is negative. Now I have an odd number of negative signs that makes this interval negative. Let's test the next interval, maybe 4. 4 plus 1 is positive. 4 minus 3 is 1. 1 squared is positive. 4 minus 5 is negative. I have an odd number of negative signs, so this is a negative interval. Something over here in our last interval, maybe a 7. 7 plus 1 is positive. 7 minus 3 is 4. 4 squared is positive. 7 minus 5 is positive. I have no negative signs, so this is a positive interval. Here, I'm saying that I want to get all the numbers that would cause this expression to be greater than or equal to 0 or positive. So I'm going to select this interval and this interval. So that would be positive. Now let's test the boundary points. If I used negative 1, if I put a negative 1 here, it causes this factor to be 0. 0 times this number is going to be 0, divided by whatever this number is going to be still 0. So negative 1 is included in our solution set because we also want to include the things that make the statement equal to 0. So I'm going to go ahead and put a square bracket there. How about 3? And I'm looking at 3. 3 plus 1 is 4. 3 minus 3 is 0, and 0 squared is 0, so I have 4 times 0 on the top, and 3 minus 5 is negative 2. So I have 0 divided by negative 2 is equal to 0. So I would include the number 3. Nothing to the immediate left and right of it, but just that number 3. Now let's try the last critical number, 5. I can see here, if I put a 5 in the denominator, it's going to cause division by 0. So I'm not going to include the 5 in my solution set. It's going to be like this. and of course with arrows on the ends like so. So this is a curious set. We'll have negative infinity to negative 1 with a square bracket, union, curly braces with a 3, union, 5 with a parenthesis, to positive infinity. So I want to solve a similar problem, but with different inequality symbols to see how that changes our solution set. We started in the last problem with a similar inequality, but we had greater than equal to 0. This was our resulting sign chart and solution set. How would it change if we had a strict greater than 0 inequality? Well, we would not include the boundaries that cause it to be 0, which would be the negative 1 and the 3. And we could not include the 5 anyway because that causes it to be undefined. So we end up with using this interval, not the boundary, not this interval, not this boundary, not this interval, not this boundary, but we can use this interval. So our solution set becomes negative infinity to negative 1, union 5 to positive infinity. Let's say that we had less than equal to 0 as our inequality instead. So we would want to include boundaries that cause the rational expression to have a value of 0. Still, we cannot include 5. 5 causes the expression to be undefined. But we're going to go ahead and include negative 1 and 3. And again, we want less than this time. Well, we know this interval tested out to be positive, so we're going to want these two intervals instead, between negative 1 and 3 and between 3 and 5. Now let's treat the boundary points. Negative 1 would be included because it would cause us to have a equal to 0 statement. So we're going to include that. 3 would be included because it would cause the statement to be equal to 0. And 5, again, would not be included because it causes that rational expression to be undefined. Now, we don't have to mention 3 because it's already included in the set from negative 1 to 5. So this changes our solution set quite a bit. From negative 1 inclusive to 5 not including the 5. Again, there's no need to mention the 3. It's already included in this set. Now let's say that we had a strictly less than 0 on our inequality. Let's start with the same boundary points that we had had. The less than means we're going to pick the negative intervals, and we don't want to include anything that causes that rational inequality to be equal to 0 because we're lacking the equal to part. So we're going to not include negative 1 because that would make it equal to 0. We're going to not include 3 because that would make it equal to 0. And we're not going to include 5 because it makes the expression undefined. So we have another different solution set. It goes from negative 1 to 3, union 3 to 5. All parentheses, not including any of those critical values. Let's solve this rational inequality. 4x plus 2 divided by x minus 5 is less than equal to 4. Now, You might have an idea that you could go ahead and multiply both sides by x minus 5 and clear the fraction because we don't like that fraction. However, we cannot do that with an inequality. The reason we can't do that is that we don't know what the value of x is. We definitely don't know what the value of x minus 5 is. Is it positive or is it negative? And that is where the problem lies. If x minus 5 is some negative number and I multiply both sides of this inequality by x minus 5, I would need to flip the inequality. If it's positive, it would stay as a less than equal to. But I simply don't know at this point. So we cannot clear the fractions. So what we'll need to do is go ahead and get it equal to 0 by subtracting 4 from both sides. So we had the less than equal to 0 on one side. And then I'm going to go ahead and combine these. Now we're just adding, subtracting fractions here. So I need to get a common denominator. 4x plus 2 over x minus 5 minus 4 times x minus 5 over x minus 5 less than equal to 0. So I'm multiplying 4 over 1 by 1 in the form of x minus 5 over x minus 5, just so I can get a common denominator. Now I can say this is 4x plus 2 over x minus 5 minus 4x minus 20 over x minus 5 is less than equal to 0. Now I'm going to have to subtract these fractions. Now remember, we have to subtract this entire numerator, not just the first term of it. So be careful here. 4x plus 2, I'm subtracting 4x, but I'm also subtracting a negative 20, and that's all over x minus 5, which is less than equal to 0. Let's see where we can go from here. Simplifying, I get 22 over x minus 5 is less than equal to 0. Now we're ready for our sign chart. We have a single fraction and a less than equal to 0. So I'm going to find my critical values. I only have one critical value from the factor of x minus 5. And my factors are 22 and x minus 5. Of course, 22 is always positive no matter what interval we're in. But let's say that we test a 0 over here. 0 minus 5 is negative. And a positive times a negative is negative, or a positive divided by a negative is negative. Let's test this interval, maybe a 7. 7 minus 5 is positive, and we have two positives, no negatives. That turns out to be a positive interval. Now, what kind of interval do I want? I want intervals that are less than equal to 0. This would be an interval that is negative. That's the only negative interval. And do I include 5? Well, 5 does not make that rational expression have a value of 0. It causes it to be undefined because it's in the denominator. So I need to not use 5. My solution set then is negative infinity to 5, not including the 5. So you can see here that you could have a less than equal to 0 or greater than equal to 0, and you won't have a square bracket in some of these. Now this is a polynomial inequality. but it's very similar in the fact that it's non-linear. So I'm going to have already factors here. I can get my critical values from those. Critical values of 2 from this one, -7 from this one, 0, don't forget that one, from the x cubed, and x minus 8 is going to give me a 0 of 8. So let's put those on the number line in the order that they would actually appear. They don't have to be scaled in any way. And I'm going to go ahead and test. Now this is one of my factors, a -1. Then I have an x minus 2. I have an x plus 7 to the 4th power. I have an x cubed. And I have an x minus 8 quantity squared. Now, we're a little bit crowded here. Let me show you a little bit of an insight here. If I am testing this factor of x minus 8, remember, it's being squared. So even if you're putting a number in here that makes it negative, this square is going to make it always positive. So if it's always positive, it's not going to have any change on the behavior of that function. We don't even have to test it. Same with this one. If the number that we're putting in for x here causes that to be a negative, remember, it's to an even power anyway, so it's going to be positive always. So we don't really need to test that. We're really just testing the things that could give us possibly a negative sign. And I know my -1 is always negative. It's constant. So we really are only testing two things. As hideous as this polynomial inequality looks, it really comes down to just these two factors. So let's test here a -8. -8 minus 2 is negative. -8 cubed is negative. I have an odd number of negatives, so this is negative. Let's try a -1. -1 minus 2 is negative. -1 cubed is negative. An odd number of negatives means this is a negative interval. Let's try a 1 here. 1 minus 2 is negative. 1 cubed is positive. And now I have an even number of negative signs, which makes this interval positive. Let's try a 3. 3 minus 2 is positive. 3 cubed is positive. I have an odd number of negative signs, so this does end up being a negative interval. And my last interval to test, let's try a 9. 9 minus 2 is positive, and 9 cubed is also positive. Still, I have this negative hanging around. I have an odd number of negatives, so this interval is negative. What kind of intervals do I want? I want negative intervals, and I don't want to include any boundaries that would cause this to be 0. It doesn't have the equal to part. So I'm going to be picking this interval, this interval, this interval, and this interval, but none of the boundaries. So I will have 4 separate intervals. Negative infinity to -7, union, -7 to 0, union, 2 to 8, union, 8 to positive infinity. And that's your complete solution set. Let's solve this nonlinear inequality. Now, again, I have not a 0 on the one side, and that's what I need so that I can determine positive and negative. So I'm going to go ahead and distribute the negative x and subtract 6 from both sides so that I can have a 0 on the one side. Now, I don't like so much leading off with a negative here, so what I can do is multiply both sides by -1. When I do that, it changes all my signs and flips my inequality sign. As long as you do that, you're still good. Now, I can factor. This is an x minus 2, x minus 3, less than, equal to 0. Let's go ahead and make our sign chart. My critical values are 2 and 3. I'm going to list the factors, x minus 2 and x minus 3. Testing 0, I get 0 minus 2 is negative, 0 minus 3 is negative, and I have an even number of negatives. That makes this a positive interval. Let's try a number between 2 and 3. 2.5. 2.5 minus 2 is positive. 2.5 minus 3 is negative. I have an odd number of negative signs, so this is a negative interval. Let's test 4. 4 minus 2 is positive. 4 minus 3 is positive. And I don't have any negative signs, so this ends up being a positive interval. And what kind of intervals do I want? I want intervals that are less than, equal to 0. That would mean this interval. And because I'm including critical values that cause that to be equal to 0, I will include the endpoints of 2 and 3. So my solution set is 2 to 3, including both of those boundary points. Here, I want to solve x squared greater than, equal to 36. You might be tempted to take the square root of both sides here, but you cannot do that with inequalities. They don't work quite the same as equations. So we have to do this the same way as we did the last one. Get a 0 on one side and then factor. X plus 6, x minus 6, greater than, equal to 0. I have my critical values of -6 and +6. And I have these factors of x plus 6, x minus 6. -7 plus 6 is negative. -7 minus 6 is negative. We have an even number of negatives, so this is a positive interval. Let's try 0. 0 plus 6 is positive. 0 minus 6 is negative. We have an odd number of negatives, so this is a negative interval. Let's try 7. 7 plus 6 is positive. 7 minus 6, also positive. And we have no negative signs, so this is a positive interval. All right, what kind of intervals do I want? I want greater than, equal to 0 types of intervals. That means positive intervals. I'm going to pick these two intervals because they tested positive. And I can include my boundary points because those boundary points are what makes this equal to 0. Okay, my solution set then is -infinity to -6 union 6 to +infinity.